Alright, so in this lesson we're going to start talking about kinetic energy and work and how they relate to one another, which I assume you know that there is a relationship between the two. Kinetic energy really is defined as energy that's associated with the motion of an object. Probably the most common type of kinetic energy we come across in physics is what we call translational kinetic energy. That's our 1/2 mv squared. That's talking about some sort of linear motion. Probably the second most common type of kinetic energy you come across is what's called rotational kinetic energy, 1/2 I omega squared, related to the rotation of objects. There are other forms of kinetic energy out there. These are the two that we come across most frequently, at least in our study of mechanics. A third one that I can think of that you've probably used before at some point deals with large collections of particles, say like a gas. The measure of kinetic energy in a gas is really related to its temperature. The temperature and kinetic energy are related to one another. So kinetic energy and work are related to one another by what's called the work-energy theorem. Basically what work does is it changes the kinetic energy of an object. That net work done in an object is equal to its change in kinetic energy. If we think about work as being forces acting on objects over a displacement, if there's a net force acting over an object over a net displacement, well, we know net forces cause acceleration, and so the kinetic energy must change because the velocity changes. So we use K to talk about kinetic energy. 1/2 mv squared, 1/2 mv squared. That's really the way we work this out. And so let's kind of work through this type of problem here and see if we can figure out let's look back at problem C2 that we had in the last lesson and see, does this make sense in the context of the work-energy theorem? So the very first thing you do is figure out what the net work on the object is, and so that would be add up the work done by all the forces. And so that's the work done by gravity plus the work done by the pushing force plus the work done by the normal force, and we actually get 0 when you do that. Which means the change in kinetic energy of this block should also be 0. Now, if we look at the problem itself, it said that this was at a constant speed, so the change in kinetic energy is 0. So kind of one of the cool things here is if we were doing problem C2 in the last lesson and we saw this constant speed piece and I calculated the work due to gravity, I would already know what the work due to the pushing force is, because work due to gravity, work due to the pushing force, work due to the normal force, those three all have to add up to be 0. Work due to the normal force has to be 0 in this case, so those two have to be the same size of number, just opposite in sign. So let's look at a second problem, and in the second problem I'm doing one that's completely symbolic. And so we have a car traveling down a level road at a speed v0 at the instant when its brakes lock up and the car slides to a stop. It says, using the work-energy theorem, determine the minimum stopping distance required in terms of v0, g, the acceleration of gravity, and the coefficient of kinetic friction, mu k, between the tires and the road. What this is telling me is in this problem, when I get an answer, I should have a distance that is an equation with only 3 variables in it: v0, g, and mu k. So let's see how we can do this problem. The first thing I would do is start with the work-energy theorem, because it tells me using the work-energy theorem, so work net equals change in kinetic energy. And what that would mean is the work due to friction, which is going to be the frictional force times the displacement s, so negative F times s. And it's really this s that I want to find, the minimum stopping distance, is equal to 1/2 mv final squared minus mv initial squared. Now if I slide to a stop, I really know what v final is. V final is 0, so minus F times s is equal to minus 1/2 mv initial squared. And so I can divide everything by the negative sign and get frictional force times displacement equals 1/2 mv initial squared. So part of my next step is to figure out what the frictional force is. And so what the frictional force really is equal to is mu k times the normal force. That's the definition of kinetic friction. And in this case I'm going on a level road, so the normal force and the weight of the car have to be the same. Draw the picture if you're concerned, draw the free body diagram, prove it to yourself that that's the case. And so you get mu k mg s times 1/2 mv initial squared. From here I can divide by mu k mg and get s by itself. I've divided out the m first because the m's on both sides, and if we look at, we have an equation based upon s, the minimum stopping distance, and the other 3 variables that I want. And so when I divide by mu kg, I get that the minimum stopping distance is v0 squared divided by 2 mu kg. Now the question that I have as a follow-up question here is, what would happen if the initial speed was doubled? Now at first glance you might say, well, then the stopping distance should be doubled, right? If you're traveling 40 meters per second versus 20 meters per second, shouldn't you travel twice as far at 40 meters per second? Well, if you look at this equation, that's not what this equation tells you. If your initial speed was doubled, that means your stopping distance became bigger by a factor of doubled squared, so really your stopping distance becomes bigger by a factor of 4. So the difference in your stopping distance between 40 meters per second and 20 meters per second is really a factor of 4. And so this is where speed, at least when you're talking about cars, when you're thinking about how far you need to stop a car, the faster you're going, the longer the distance is, and it's not a linear relationship, it's a square relationship. So the difference between, say, 20 and 40 is a factor of 4. I mean, when you start to get to large numbers, the difference between something like 40 and 45 is much bigger than the difference between 20 and 25, because those squares are much bigger. So there are some interesting things that start to happen when we start to play around with this. We can also see that as the coefficient of kinetic friction decreases, your stopping distance increases, and that is a linear relationship here, or that's an inverse relationship, excuse me. So let's take a red wagon with a mass of 10 kilograms and it's moving at a speed of 4 meters per second on a horizontal surface, and a net force of 5 newtons is going to push on it for 6 meters in the direction it was originally traveling. And I want to know what the wagon's final speed is. This is a pretty straightforward work energy problem. You know the mass, you know the initial velocity, you know the force, you know the displacement, calculate the final velocity. So work net is equal to mu delta k, so the force applied times the displacement, they're in the same direction, so there's no directional component, equals half mv final squared minus half mv initial squared. Divide everything by m so that I can try to get the v's by themselves since I'm looking for v final. Also multiply everything by 2. Add v initial squared to both sides. And here I now have the equation in terms of v final. 4.69 meters per second is the final velocity of this cart. Now this doesn't seem like a very big change in speed, does it? We went from 4 meters per second to 4.69, and I have this force that's acting on the cart for 6 meters. And 6 meters is a pretty decent distance. At least I would think of it in terms of a 10 kilogram wagon. That's not too bad of a distance. And 5 newtons maybe isn't that gigantic of a force, but let's see if it works out by using Newton's second law in kinematics. So force equals ma, so we can calculate the A. Well, 5 newtons divided by 10 kilograms is a half meter per second. And we have 2ax plus v initial squared equals v final squared. Well, that's easy enough to solve for v final squared, just square root both sides. And if you plug in all your variables, you actually end up with the same result, 4.69 meters per second. You can even substitute this in for a if you would like, and end up with the same exact equation. So it doesn't matter which way you do this problem. Either way, you're going to get the same result. And so in a problem like this, there's actually 2 different ways you could conceivably solve it. Work energy theorem, Newton's second law in kinematics, and both give you the same result. Now in physics, we like it when this happens, when you can use multiple paths to get to the same answer and the same result. That tells us that, well, our systems that we use here, Newton's second law, kinematics, and work energy theorem all agree. That means it's more likely that those ideas are valid ideas that work mathematically for a larger variety of systems. So just kind of a quick overview of work energy theorem. We'll start to look at in kind of the next set of lessons is work done by specific types of forces, and then we'll look at conservation of energy.